So hello everyone, I'm Jean-Philippe Bossuat, a cryptography software engineer at TuneInsight. I'm a co-author and currently maintainer of the Lattigo library. Today I will present Lattigo v5. It will be a presentation that is at the same time both what is new in the v5, but also an overview of current state of the library. So I have a chat open, and if you ask questions, I will try to answer them in real time. So I will start with a general introduction about the library, its origin, and its current state. And then I will go over the packages, explaining what the packages does, and with some small code snippets to illustrate some API examples. So first, Lattigo, it's an open source Go module that was first published in 2019. It was initially developed at the Laboratory for Data Security at EPFL, to supplement the work of the PhD student and enable them to implement their research. Afterward, it was taken over by TuneInsight, which currently continues its development and maintenance since 2022. It's licensed under Apache 2.0. About the usage and community. So it's a community open source version of the TuneInsight library. It recently broke over 1,000 stars on GitHub. It's also a yearly contender in the Adash competitions. So by that, I mean that every year you have at least 1-2 solutions that use Lattigo among the winning solutions that use Lattigo. We have heard a lot of good feedback from the academic community when going to conferences. It's often used to prototype their work. And it's also listed on the Amazon Web Server cryptographic computing with C++ bindings. For anything related to question, contribution of new feature, proposal, or request, you have a GitHub discussion and issues, and you can also mail us directly if you want to keep it private. So what does it do? Lattigo implements all mainstream full-LNS ring learning error schemes, and also their multi-party version. It's designed to be modular, and it's constructed around a layered architecture that enables fast prototyping for RWE-based schemes. By this, I mean that each layer is a skeleton of the layer above, and you can go really deep, like just having the base arithmetic, but it's not even cryptographic if you want to prototype something new. And it's used Go because Go, it's a cross-platform language. It can compile into WASM, and it has a very good performance that are often comparable to C++ libraries. So about its capabilities, it implements full LNS arithmetics over the cyclotomic rings and its conjugate invariant, which is a special case. It has a scheme-agnostic RLW-based primitive like key generation, encryption, decryption, key switching, automorphism, and other operations. By scheme-agnostic, it means that it doesn't matter what scheme you use can use these primitives, and they will interoperate between schemes smoothly. It also provides the multi-party T out of N threshold key generation, proxy encryption, and interactive bootstrapping. It has a unified version of BGV and BFV for arithmetic over modular encrypted arithmetic. And it also implements fixed point approximate arithmetic over the complex and the real numbers. Recently, it has also we also added support for ring GSW ciphertext along with external product and blind rotations, which make it more or less complete of what is actually available. This is its layered architecture. So each node is a package, and package have dependencies. And now I will go over each package, explaining what it implements with some code to showcase the API. So we start with the ring package. This is the lowest level, and it implements the polynomial arithmetic. So what it provides is operation over the ring of polynomials, the automorphism, the number theoretic transform, sampling prime, very low-level modular arithmetic, also RNS basis extension and reduction, RNS division, and the sampling of course, like Gaussian ternary and uniform, which are the most common sampling, and also polynomial interpolation over ZQ. So here is a small example of how to instantiate a ring. So just a disclaimer about the code. To make it readable, often it will not compile. But this is a showcase about the available API. So you would first decide your ring degree, and then what is your nth root of unity, the size of your prime, how many primes you want, and then generate the primes, instantiate the ring, and with that you can now also instantiate a subring that is it has no memory allocation, but it allows you to operate at the specific levels. And from that, you can allocate new polynomials, and this is a small example of doing a neg-acyclic convolution between two polynomials. So you switch them in the entity domain, you switch one of them in the Montgomery domain, you do multiplication, and you switch them back. It has also the API for other more generic operations like the automorphism, RNS division, and RNS basis extension, the sampling, and the interpolation. So we try to make this as easy as possible to be used, so that you can use this layer to implement or prototype something that will not be RLW based or would require something very low level to start with. Then we have a package RLWE, and this package, it implements all the features that are scheme agnostic. So this includes the parameterization, the key generation, so the secret key, the public key, and all the evaluation keys you could think about, encryption and decryption. It defines what are plain text and ciphertext, and the keys also. And it has a generic evaluator that provides a RLW-based arithmetic. So the gadget product, automorphism, you have a trace, but you also have more advanced operation like ring packing and ring dimension switching. This is a code that showcases how you would instantiate RLW secure instance. So in the parameters, you have to specify the log of your ring degree. You can specify the size of the prime, how many prime you want, and also the distribution of the error and the secret. Right now, we support 3 distributions, which is Gaussian, discrete Gaussian, ternary, and uniform. And also the entity flag is if you want or not to your value to be by default in the entity domain or not. And then you can also print some information about what RLW instance you instantiated. And this is an example about how you would generate the keys. So you first need to instantiate the key generator from the parameters. Then you can generate a secret key. From this secret key, you can generate a public key. Actually, you can generate as many public keys as you want from the same secret key, which is something that is not available in other schemes. The relinearization key, and then the Galois keys from your Galois elements. And something that is new in the v5 that you can now specify exactly at which level and which base of 2 decomposition you want the key to be. This enables really fine granular parameterization of the key to optimize the memory or the noise for specific operation. Before, you had to specify this in the parameters, in the RLW parameters. And if you wanted to change that, you needed to instantiate new ones, and it was really not convenient. Now, it's an optional parameter. If you don't give it, then if you just put everything at the maximum available values. But now you can also generate the keys with specific parameterization. And now some example how you would encrypt and decrypt values. So it's really always the same. So you have a new encryptor, new decryptor to instantiate this object, and then you can just call encrypt or decrypt on a plain text or a ciphertext to do this operation. And for generic elevators, you have to give it the keys, and then you can call evaluate with some specific key, or apply an automorphism, or apply the trace, etc. Now we switch to the ring GSW package, which is a specific package instantiated that use the RLW package as the backend. And this is very short. This package implements definition for ring GSW ciphertext, plain text, encryption, and the external product that is at the core of blind rotations. So the API is the same as the RLW package, except you have a prefix RGW, basically. And the external product, of course. So a thing that is specific to Lattigo is that each package, or sometimes each operation, has its own evaluator when it is a heavy operation. And for example, here, to do the external product, you have to instantiate an RGSW evaluator. So it turns out that this is just a wrapper of the RGSW evaluator with another additional method. So you don't allocate more memory by doing that. Now we switch to the schemes. So the CKKS schemes and BGV schemes. This package, they implement the parameterization of the scheme, the encoding and decoding, and the homomorphic operations. All the rest is still implemented in the RGSW package. So everything related to encryption, decryption, etc. And key generation is still from the RGSW package. This enables a really smooth interaction between multiple schemes if you need to. Yes, can I explain the structure of Galois keys? I think this is too specific of a question for me to answer now. Maybe the question is too broad, but we can take it after the presentation. And so each scheme has its own evaluator with the homomorphic operations, but since it is also a wrapper of the RGSW evaluator, it also has access of all the methods of this evaluator. And in the V5, we made it so that the encoder and evaluator of all the schemes, they share a simple and common interface. This means you can now design circuits that are independent of any schemes just by using interfaces. In Lattigo V5, we have something that is new, which is that we implemented a journalized variant of the BAV and BGV schemes under a single scheme. So the original BGV scheme is seen as LSB encoding, so least significant bit encoding. So to do that, you scale the error instead of scaling the message. And the BAV scheme, is the opposite. You scale the message and don't scale the error. So they are often described as two different schemes, but in fact, if the plaintext modulus T is coprime with Q, then you can just set the scaling factor to be the inverse of T modulo Q. And then a BAV ciphertext becomes simply actually a BGV ciphertext that is scaled by T-1. So BAV and BGV ciphertexts are equivalent up to a scaling factor, which means that you can define the BAV style and you can define two tensoring style on the same ciphertext. So we still have a BAV scheme in the library for backward compatibility, but now it is instantiated as a BGV scheme, as a wrapper of the BGV scheme with the multiplication that is restricted to only the BAV1. And so something that is new is that we now support sparse packing. So if you happen to give a plaintext modulus that has a 2n fruit of unity that is smaller than the ring, the 2n fruit of unity, it won't throw an error anymore. You would just have less slots available. So this is an example of the BGV scheme with two different tensoring. So we have the regular BGV or CKKS style tensoring with the rescaling, which is just you multiply and then you have to rescale. But if you want to do a BAV style tensoring on the BGV ciphertext, you can call Muller-Redin scaling variant, and it will do this BAV style tensoring. On the side of CKKS, but also the other scheme, Lattigo V5, it brings two major improvements. One is drastic reduction in the API and to minimize and simplify the interface. For example, before, all these 6 methods, so negation, multiplication by a constant, multiplication by a Gaussian integer, multiplication by the imaginary unit, division by the imaginary unit, or multiplication between plaintext and ciphertext, they are all implemented with separate methods. And now they have all been consolidated in the same method, which is mul or Muller with relinearization. And this API simplification was applied to, this style of simplification was applied to both the evaluator and encoder of all the schemes. And we also now support quad float precision for CKKS, so with scaling factor of up to 2 to the 20. So this is an example of how this new API works. So with the same method, you can give as a middle operand pretty much whatever you want, and it will act accordingly. An advantage of this is that you can now have interfaces between schemes. So you can define an interface for an evaluator that is independent of the scheme, and also, again, design a circuit that is independent of the scheme. And then give any evaluator that complies to this interface to be evaluated. Now we go to the package HE, which is actually a package that implements everything that is scheme agnostic and high-level functionalities. So it has mostly interfaces, for example, a bootstrapper interface for encoding and evaluators, but also generic linear transformations and polynomial evaluation. So you have these circuits that are scheme agnostic, and they will work as long as you provide an evaluator that complies to the interface. What this does, it enables to reduce the code redundancy between schemes, and also enables the user to provide custom implementation of subroutines of this algorithm, for example, through interfaces. So this is an example of one of the interface for bootstrapping. So you define your interface, and then you can define any type that you want. Here it's called ciphertext type, just to be explicit about what it should do. And then your bootstrapper should comply to this interface. So you should have a method that does bootstrap, takes a ciphertext, return this ciphertext and an error, etc. And once you have bootstrapping that complies to its interface, you can really easily implement and debug schemes that need bootstrapping, for example, by defining dummy bootstrapping or interactive bootstrapping that complies to interface and use it as plug and play for your circuit. So first design it with by defining this interface, and then giving a dummy bootstrapping when you test it, and when in production you can actually give the actual bootstrapping that complies to its interface. Now HEBin. HEBin is the package that implements blend rotations. So in this V5, we provide the LMK CDay blend rotation. This is a new algorithm that has really nice properties for blend rotation. So the idea is that we always want to evaluate the product of the public part times the encrypted secret key at the exponent of some polynomial. And what they do in this work is that they define this product actually as a sum of polynomial in the basis -1 and G in the generator of 2 and star. And they use automorphism and external product to evaluate it. And the advantage of this approach is that it completely decorrelates the complexity of the blend rotation from the distribution of the key. And this makes it suitable for threshold FHE, which was not the case before, because you needed to have key with very specific distribution for it to remain efficient. So this package, it implements blend rotation over RLW samples. So we don't have yet ciphertexts that are defined for LW sample, but it will come at some point. And it also has a method for automatic sample extraction and ring packing with sample permutation. So you give an RLW samples a map of test vector, and then it will automatically evaluate the test vector on the LW samples, repack them, and give you back an RLW samples where in each slot that you choose, you have the evaluation of this lookup table. So it's a code example of how you would evaluate blend rotation on some LW sample. So you have to define again the evaluation key. So this is the same interface. It reuses the LW package for the evaluation key parameters. So in this case, we set the base 2 decomposition to 2 to the 7. You generate the evaluation key by giving the parameters of your test vector and the parameters of your LW samples, along with the secret keys, associated secret keys. And here we have an accumulator that is a dummy accumulator, but you would instantiate it to what is in the comment, and then you can call blend rotate core, and it will evaluate the blend rotation. And now HEInt, which is the package for the front. It's package that is internal to the front end of the library for encrypted arithmetic over encrypted modular arithmetic. So it's a package that wraps package BGV, LW, and HE. So its functionalities are the same. It's encoding and decoding with the homomorphic operations like addition, multiplication, rotation, and rescaling. But it also has, on top of it, the linear transformation and polynomial evaluation that are instantiated using the generic implementation of the package HE. And of course, it has all the methods of the RW evaluator since they are available by default. And as always, the key generation, encryption, and decryption are done using the RW package. And it's interface-based. So all the method and evaluator are interface-based. So it's very easy to provide a custom implementation of all these subroutines. For example, if you want to add concurrency or some hardware acceleration, you can easily do that for interfaces. Yeah, this is an example of the homomorphic operations that are available. So addition, multiplication, rotation, relinearization, and etc. Now the HE float, which is the front end of the library for fixed point encrypted arithmetic over a complex number over real numbers. Like the HE int, it is a wrapper of the CKKS scheme, the HE package and RW package. It provides encoding and decoding. And for the homomorphic operations, as usual, the addition, multiplication, rotation, and rescaling, linear transformation, polynomial evaluation. We also have homomorphic encoding and decoding if you want to switch between plain text domain, the homomorphic modular reduction, and recently we also added methods to evaluate the sign, the step function, minimum and maximum, and also division. And yes, usual, key generation, encryption, and decryption are all done using the RW package. And like the HEIN package, it's all interface-based, so you can easily plug and play your custom implementation of any of these subroutines. So by subroutines, I mean if, for example, if you want to evaluate the sign, you would instantiate a sign evaluator, and it requires to be given some interfaces. And so by default, you can use the original evaluator, but you can also define your own and give it to it. As long as it complies to the interface, it will work. And by doing that, you can provide your own custom implementation. So this is an example of the API. So we tried our best to have the API between the scheme to be exactly the same. And yeah, this is an example on how you would evaluate, for example, the sign on a ciphertext. So you would instantiate the comparison evaluator by giving the cryptographic parameters, your current evaluator, and a bootstrapper if needed or not. And so yes, it also needs a polynomial for the sign, but it's optional. You can also omit this if you just want to use the default capabilities. And then you can simply call sign, step, or max on the ciphertext. And you can even do some more advanced arithmetic. For example, in the RW package, you have what is called an inner function. So it's a generic evaluation of RW ciphertext that will take as input a function with 2 inputs and 1 output. And here, if you give a max, then it will compute the max across all the values of the ciphertext. So it's the same as an inner sum, except by doing the sum, you do some function over the 2 inputs. So yes, all evaluators of the HEINT and HEFloat package are interface-based with public fields. So you can provide custom implementation for each subroutine. For example, here for the linear transform evaluation, you need to provide some evaluator for diagonal matrix. And so one is provided in the library, but if you want to provide one with concurrency, then all you need to do is write your own and make sure that it complies to the following interface. And when you instantiate your evaluator for linear transformation, you just assign your interface to this field, and it will use it. Now we go to bootstrapping, my favorite part. So we have we implement the bootstrapping for approximate homomorphic encryption, so the CKKS scheme, and the v5 brings a lot of improvement and usability. So now we have an automatic management of the bootstrapping parameters and evaluation keys. So everything is abstracted from a user. I will show it in the code snippet afterward. It supports both the original CKKS and its real variant. It has batch bootstrapping of ciphertext of lowering degree, with or without sparse packing, with an automatic packing and unpacking that is depth 0. And it has up to 16 tunable parameters if you really want to deep dive into how you would parameterize it. But you can also use default parameters and it will work fine. And it has full support for meta bootstrapping, which provide arbitrary precision bootstrapping. By default, if you don't specify anything in the parameterization, it will be a depth 15 circuit that outputs an average bit precision of 27.25 for complex value uniformly distributed in -1 and 1. And it has a failure probability of 2 to the minus 138 for 2 to the 15 slots. So here's how you would instantiate a bootstrapper. So first you define your bootstrapping parameters. Here we leave a field empty because we don't want to specify anything fancy, and we will use the default parameters which provide these performances. You need to generate your bootstrapping parameters. So it will generate them from your residual parameters. So this is what you want to remain after the bootstrapping. And the parameters literal, which define the specificities of the bootstrapping circuit. Once this is done, from the bootstrapping parameters, you have to generate the bootstrapping keys and then instantiate the bootstrapping evaluator with the keys. And afterward, this evaluator comply to the bootstrapping interface of the HE package. So for example, you can call bootstrap or bootstrap many to bootstrap a list of ciphertext. Now we switch to the multi-party package. So the MHE package, it implements ring LW-based multi-party morphic encryption primitives. So it provides generic interface for the local steps of N out of N and T out of N multi-party morphic encryption MPC protocols that are common across all the early distributed schemes of Lattigo. So this means the collective public key generation, the collective allocation key generation. So subcategories, you have a collective realization and Galois key generation. You have also key switching from a secret share secret key or key switching to a public key, so proxy encryption. And also a T out of N threshold divisor if you want to first secret share in a Shamir way the secret key to ensure that if at least T party out of N are present, you can still do all these operations. So this is an example of how you would generate a public key, so a collective public key. Each party would instantiate the collective key generation protocol, and then it would give us as input its secret key, common reference string polynomial, and its share, and then all the party will aggregate the share, and finally they would generate the public key from the aggregated share. So this protocol have a public transcript, so all you need is an authenticated channel for it to be secure. And we have the equivalent of the HEFloat and HEIN package, but with their multi-party version. So since everything that is related to key generation is independent of the scheme, this package will implement things that are specific to the schemes, and this is collective decryption and re-encryption from linear secret sharing shares, and the collective, so interactive bootstrapping, with also an arbitrary public linear transformation in the middle if you want to. So this is the example of the collective bootstrapping with the linear transformation. So you would define your linear transformation as a function on the coefficients. And if you want or not to encode or decode the value before you apply the function, each party would generate the share. You can also actually, so you have two public keys because you could re-encrypt to a different set of parameters, but if you don't want, you just put the same. And once you generate the share, it will deaggregate the share, and then the party that does the refresh, it will take the aggregated share, do the public decryption in the secret share domain, apply the linear transform, and the public encryption from the secret share domain to irreducibility domain. And that's all for the cryptography package. And then you have some utility package that are new in the V5, and they're actually very useful in practice. So the first one is the buffer, util buffer. So this defines interface to write and read on readers, so for serialization. And what is new in the V5 is that all the objects now, they comply to this interface. So EO writer, reader from, encoding binary marshaller and binary unmarshaller. and the binary size, which returns the size in bytes. And so what this package do, they allow really easily serialization of all the objects. So if you have any value or any slice that can be stored on, for example, Uint64, you can write it on a, marshal it on a writer that has pre-allocated bytes, or read it from a reader. And so as a bonus, we have a method that can test if the object that you implements this interface, and it will test everything that is correct. So for example, that when you marshal it, it marshals the outputs has the correct number of bytes, that when you reconstruct it, it is the correct object, and etc. The package struct, it implements generic structs like matrix, vectors, or maps over object that implements this interface. So before, if you had a matrix of ciphertext, marshalling it was quite painful because you would have to read the number of lines, write how many rows, the size of each row, etc. But now all you have to do is, okay, I have a matrix of ciphertext, so I will just instantiate, so it's a vector, sorry. A vector of ciphertext, so I will instantiate it as a struct.vector with a type RLB ciphertext. And now I have access to all the methods that are implemented by this interface. So I can see what its size would be if I marshal it. I can write it or read it from a buffer, and I can also use the generic marshal binary and marshal binary from Go. And you have some other methods like deep equals or copying the object to compare. This really change, make our life much more easier when implementing like real life use case, when you have to serialize the data and unserialize it. And some new things in the Bignum package, which implements arbitrary precision over complex arithmetic. And it also provides polynomial interpolation. So here you have an example of multi-interval minimax Remez polynomial interpolation, which allows you to interpolate any smooth function, any function that is smooth over discrete intervals. And you can use that to interpolate your polynomials and then evaluate them, for example, with CKKS scheme. So voila. So Lattigo has a modular architecture, and it has quite advanced capabilities that enables fast prototyping for efficient and scalable RLB-based single and multi-party cryptographic applications. You have many actual examples in Lattigo dash example. So all the codes here were just to showcase the API. It probably will not compile, but if you want actual example, you can go there. So this is a community version of Lattigo, which means that anyone can contribute, provide ideas or documentation, etc. And we would be happy if we had more feedback on who we use the library. And we are always happy to have proposals for new functionalities, algorithm, and optimization. Of course, you are always welcome to participate on the GitHub discussion, ask your question there. And thank you very much.